which indicates that the video is being recorded at the top of my screen, that on the left. Can you acknowledge whether?
Yes, sir. Recording is started.
Okay, so can you see the red button at the top left, sorry, top right of the screen?
Yes, sir.
So that is the video recording indication, is it?
Yes, sir.
Okay, good. So just a recap of what we have done in the last couple of lectures. We started with strings over an alphabet and languages. So we defined these two notions. Then we defined what is a DFA. Then we defined what is the notion of acceptance. The language accepted by M, which we denote by LM. And then we define the notion of a regular language. Right? So we say that L is regular if there is a DFA M such that L is accepted by M. And then we saw some examples. Right? So does anyone have any questions or doubts about any of these concepts? So LM, by definition, remember, is the set of all strings W belonging to sigma star such that M accepts W, which is the same as saying delta hat Q naught W belongs to F. Yeah? Any doubts? If not, let us continue with a couple of more examples. One of the uses, one of the very old uses of finite automata is recognition of strings or pattern recognition. Okay. For example, the kind that is used in the Unix command grep, right? Now, in your data structures course, you may or may not have come across the Knuth-Morris-Pratt algorithm, also known as KMP, the Boyer-Moore algorithm for string matching. Okay? And those are based. Can we set all? Sorry, can you repeat the question? Just turn on your mic and
Sir,
say it aloud. Yes.
Sir, in DFA, like we have our tuple of 5 parameters, right?
Yes.
Can we set the transaction function's initial state and the final state such that our for our language, these all parameters are satisfied and the language get accepted. Like we can we set that arbitrarily?
I didn't quite follow your question. When you define a DFA, you fix all these five parameters, as you say. So Q, sigma, delta.
Like if we have already defined this DFA, then we will check whether a language is followed, accepted or not. No, sir.
Yes.
And
So
so
given
if
a
we have defined it and we have a language in our hand, then can we set the parameters in such a way that it is accepted and can we call it regular?
yeah. Uh, so suppose you have to show that suppose I give you a language. It's not that you have to, but one of the obvious ways is I should say it is enough, because there are other ways of showing that a language is regular. But the most direct way of doing it is to come up with an M such that L is LM. I guess that is what you are asking, right? Is that right?
Yes, sir.
So suppose I give you a language. I can give a mathematical description or a description in English, right? So one of the ways to show that the language is regular is to come up uh, with such a DFA which accepts that language. How do you show that a language is not regular? Well, we'll see some properties of regular languages, which will help us to do that. Okay. So not all languages are regular, as we shall see. And there are ways of showing that. And we'll learn all those techniques in a moment. Okay. So let us continue with an example from string matching. So let's just define the notion of substring. So we say that U is a substring of V if there are strings UVWX, say W1, W2, such that V is W1 followed by U followed by W2, right? So this is what we mean by substring. In other words, U occurs somewhere within that string, right? Within that string V. Then we take this example. Again, our sigma is the binary alphabet, and L is the set of all strings that contain 001 as a substring. In other words, 001 occurs in that string. So for example, I have to stop these alerts on my iPad because it is really distracting. I'll do that sometime. So for example, 001 itself belongs to L, 1001, 1 belongs to L, 0011 belongs to L, and so on. Whereas 11100 does not belong to L, right? So how do we show that L is regular? Well, we have to come up with a DFA, and we'll use the graphical notation because that is most convenient, especially for small examples where the number of states is not too high, right? And that will be the case for almost all our examples, right? So to come up with such a DFA, what we need to do is we need to keep track of how many symbols in this pattern. So this is the pattern. That is 001. So we need to keep track of how many symbols in this pattern we have seen so far, right? And so we may have seen when we start off, we haven't seen any symbol in this pattern. And then we may see a 0 and expect a 0 as the next symbol. And when we see the second 0, we expect a 1 as the next symbol. So we keep track of all this in the finite state memory. And to do that, this is the DFA that suggests itself. So you have, this is 0, and this is 0, and this is 1, and this is the final state. And this is the only final state we need. And once we need that once we reach that final state, we can just stay there. Because once the pattern has occurred, it has occurred, right? That string should be accepted. And let us make this the initial state. And we have to add all the missing transitions. So let's call it Q0, Q1, Q2, and this is Q3, right? So what are the missing transitions? From Q0, we have a transition on 0, but we need a transition on 1, right? So where should the transition on 1 go from Q0? Anyone?
So sales
Stay
loop.
at Q0 itself.
Back to Q0, right? Once we have seen a 0, so in state Q1, we remember that we have seen the first symbol in the pattern, and we are expecting the second symbol. So if there is a 1 here, where should we go?
Q0.
Back to Q0, right? Because we have to start all over again, looking for the first symbol of the pattern, which is a 0. And similarly here, right? So now we have a DFA, right? Right? Any questions?
Sir, if after two, sir, you made two separate one
Right,
outgoing
right.
ones.
This is missing, right?
Sir, I have a
Right?
doubt.
And here, from Q1, it is complete. From Q2, on a 0, I should go back to Q1 because I've seen 2 zeros, right? When I'm in Q2, I've seen 2 zeros. And if I see one more 0, that still means I've seen 2 zeros and I'm waiting for a 1. Yeah. So is it complete now?
Sir, can we make a self loop at Q2 if we find a 0? Because ultimately it's multiple zeros, and whenever
Oh,
it's 1, then
sorry.
we can find 001.
Yeah. Sorry, that was a mistake. That was a mistake. So in Q2, so let me just explain what these states mean. In Q0, I'm waiting for the first symbol in the pattern to occur because everything seen so far does not match the pattern and or any of its initial prefixes. In Q1, I've seen the first symbol of the pattern, waiting for the second symbol. In Q2, I've seen the first 2 symbols of the pattern and waiting for the third symbol, right? And in Q3, I've seen all the 3 symbols in the pattern, right? So that's the meaning of these states. And now you can explain why I should remain in Q2 when I see a 0, because I've already seen 2 zeros. If I see one more 0, that means I've seen the first 2 symbols of the pattern. Yeah? Any questions about this?
So,
And
sir, if
yes,
there is a 1, it would not lead to Q0 from Q2.
yeah, right. Thanks for pointing that out. So is it correct now?
Yes, sir.
Right. Okay. So let's take another example. So you need some practice with all these examples. And that's that's a good thing to do. So you should try to solve as many problems from the book on your own to understand this concept of um, DFA and regular language. Okay. Suppose L is the language again over the same alphabet, the binary alphabet, of all words where W is the binary representation of a multiple of 3. Okay. So L should have the following strings. It'll have zeros because 0 is a multiple of 3. Then 1, 1, because that's 3. Then 6, which is 4 plus 2 plus 0. Then 9, which is 8 plus 1. Right? And so on. And of course, if you add zeros in the beginning, uh, that should not make any difference. Okay. So you can pad zeros to the left and they should still be accepted. Right? So all multiples of 3. Okay. So how do we go about designing a DFA? And by the way, notice that epsilon is not part of the language. Okay. It should have at least 1 bit. Okay. The empty string is not part of the language. The empty string is not a multiple of 3. I mean, some books, they'll provide a DFA uh, which also accepts epsilon, but that's not correct. Anyway, so what is a good strategy for coming up with a DFA for this language? Well, if you think about it, when you divide a number by 3, there are only 3 possibilities: that the remainder is 0, or it is 1, or it is 2, right? So and we are just talking about the natural numbers here. There are no negative numbers. So we are talking about only the natural numbers, starting with 0, 1, and so on. So if we can devise 3 states to keep track of the remainders when divided by 3, right? So if x is congruent to 0 mod 3, that would be a final state, right? So let me write it this way. Uh, uh, I write this state as 0, 1, and 2. So this state 0 stands for all numbers that are congruent to 0 mod 3. And so this should be the accepting state, the only accepting state. And the other two are non-accepting states, right? Then we have to figure out when do we go, where do we go when we see a 0 here, okay? We'll come to the initial state later. Let's just concentrate on these three states, right? Now you know that when you append a 0 to the right of a binary number, that's just multiplying it by 2, right? And adding a 1, if you append a 1 to the right, that is 2x plus 1. And if you append a 0 to the right, that is 2x, right? So if you have a number which is congruent to 0 mod 3, that is a number which is divisible by 3, if you multiply by 2, it still remains divisible by 3. So this is the transition on a 0. And what about on a 1? Well, then it's three times, sorry, it's 0 times 2 plus 1, which is 1. Yeah. Any questions? Yeah. I'm just reading the number from left to right. So if I encounter a 0, that means I have to multiply that number by 2. And if I encounter 1, that means I have to multiply by 2 and add 1. So if I have a number which is congruent to 0 mod 3, appending a 0, multiplying by 2 gives me a number which is 0 mod 3, which is congruent to 0 mod 3. And appending a 1, that is multiplying by 2 and adding a 1 gives me a number which is congruent to 1 mod 3. Yes? Okay, what about 1? What happens when I encounter a 0? Which state should I go to? Yes? I don't see the, can you just say it aloud? On a 0, from the state 1 on a 0, where should I go?
Sir, 2.
Yes.
2, because it is just 2x, right? So this is on a 0. And what about a 1?
0.
It is 2x plus 1, which is 3, which is congruent to 0 mod 3. Right? Okay, let's focus on 2. So if I get a 0, that means I have to multiply by 2. So 2 times 2 is 4, which is congruent to 1 mod 3. Yeah, I'm coming to the fourth state in a moment. Let's just concentrate on these states for the time being. Okay, so on a 2, when you are in state 2, you get a 0. That means it is 4. 2 times 2 is 4, which is congruent to 1 mod 3. And on a 1, 2 times 2 plus 1 is 5, which is 2 mod 3. Okay. Right. So these are all the transitions among these three states. Now you have to decide which is the initial state, and actually none of these states can be called initial, because, well, this cannot be initial because um, then it would accept, I mean, the state zero cannot be initial because then you would accept the empty string. Can any of the other two states be initial?
Sir, there is a raise of hand.
Sorry?
There is a raise of hand, sir.
Hello, sir.
Yes, you are having problems with the audio?
No, no, sir. If the input at congruent one is 0, then sir, there's two output that's going on. I mean 1 to 0, 1 to 2. So I think, sir, from 1, if the string is 1, then it should go back to 0, sir. I guess. Is it correct? Or for the same state of string, so it's going to two, states. Is it possible?
You're right. So I don't know why I drew that. I was just careless. So is it correct now?
So when it would 1, it would go back to 0 from 1. It should have been 1 instead of 0.
Yes, sir.
No, sorry. So from one, what happens if you get a one? So you get a three, right? Because 2x plus 1 is 3. So my God, this is what you meant. Okay. So is it correct?
Yes, sir.
Well, to complete the automaton, you need to add one more initial state. Let's just call it, you can call it anything. So Q0, right? So on a 0, you should clearly go here. And a 1, you should go there. Right? So now the thing is complete, right? Any doubts about this?
Sir, can we have multiple DFA for the same language? I mean, a complex
Yes.
one, sir. Is it possible?
Yes. It's possible.
Okay, sir. Thank you.
But in fact, this particular one is the smallest DFA for this example, okay? Meaning the smallest number of states. And later on, we shall see a procedure for minimizing the number of states of a DFA. So we'll come to all that. So that's multiples, and yeah. How much time? Okay, we have some time. So here's another example, and this example illustrates that sometimes it is helpful to have the states with structure. Okay, so far we have just been calling them Q0, Q1, etc. But sometimes it helps if you give them some structure. Okay, and here's an example. Okay, it's the same alphabet. And we have a language called ln. And this is the set of all strings over the alphabet such that the nth character from end of W from the end of W is 1. Okay, and here n is fixed. For example, if you have L3, right? So all words in this language will have at least 3 characters. And the third character from the end must be a 1. So 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, and so on. Okay. So here we are asked to show that ln for a fixed n is regular, right? So are you clear about the language? The set of all strings such that the nth character from the end is a 1. Okay. So here's the idea. We come up with a DFA MN, which is, of course, has all these 5 parameters, and we need to define each of them. The idea is a state in MQ remembers the last n characters. Of the input word of the input string W. Okay. So how does it do that? Well, we have to do it formally, of course. So mathematically, Q so this is the formal definition of Mn. Q, the set of states, is actually a string. It's a sequence, right? Where W is a string, right? I have enclosed this W in these angular brackets, but it's not really necessary. I mean, the set of states can also be a set of strings, okay? And that is the point behind this example. So we can give some structure to the states, right? And we need to remember at most n characters. So the length of W is less than equal n. So remember this notation. I don't know whether I introduced earlier. This is the length of the string W. Okay. Now tell me, why is it less than equal and not equal? Can you tell me why?
We may not provide n input, like we can provide less than that.
Right. No, when we start scanning the input, I mean, there are, we haven't seen the n characters, right? So we start with, we haven't seen anything at all, and then we have seen one character and two characters and so on, right? So that is why we need less than equal, right? So that's the set of states. The crucial thing, of course, is the transition function. Right? So here, the state is actually a string, W, of length less than equal n, and you get a symbol A, whether it's 0 or 1, right? So which state should you go to? Well, if you have seen less than n characters, then the state you should go to should remember W as followed by A, right? Because you have not yet reached the state where you remember the last n characters. If the length of W is strictly less than n, okay? So you remember, you add one more character that you need to remember. And otherwise, if the length of W is already n, what you need to do is drop the first character, right? And remember the second character onwards, right up to Wn, followed by A. If W is of length n, and the characters in W are W1, W2, and so on up to W. Does this make sense to you? Do you understand what is going on? For example, if n equals, maybe I should take a small n, 2, right? The set of states is let me put 0 first. Yeah. So there are these 7 states. Yes. And the transitions will be something like I'm not putting those. If you want, you can put those ovals here. On a one. So you see the idea. This is the initial state. So at the beginning, I have not seen anything. When I've seen zero, I keep it in that is stored in memory. So this state says I've seen only one character and it is zero, and this state says I've seen only one character and it is one. And on a zero, uh, this will go to 0, 0, and on a one, this will go to 0, 1, and on a zero, this will go to 1, 0, on a one, uh, 1, 1, right? And from, did I miss a one here? And from here, if you get a zero, you go back to that state. And here, if you get a one, you come here. And here, if you get a, sorry, on a one, you come here on a one. So from here on a one, you come to 1, 1. On a zero, you come to 1, 0. And from 1, 0 on a zero, you go back to 0, 0. And from 1, 0 on a one, you go to one. And what are the final states? Remember, the language is defined as the nth character from end of W is 1. So here n is 2. So these are the, that means the second character from the end must be, right? So to complete the definition, Q0, the initial state is this. The set of final states is all those strings which begin with a 1 followed by any n-1 symbols, right? So all these WIs are arbitrary. For for I between 2 and n. So any questions about this? It should be clear, right? So we are remembering what we have seen, the last n characters in the state. Okay. This is similar to the last example where we kept track of congruence modulo 3, the classes. It is similar, okay? But here there the states where the congruence classes plus an initial state. Here, the states are the strings, the last n characters in the string. Up, and of course, it could be less than n also. Yeah. Any doubts about this? Okay, I guess not. Then we come to our first non-trivial result. And that is, let's just call a proposition. Call it a proposition. Any machine or any DFA recognizing this language ln must have at least 2 to the power n states. Okay. Of course, you can check that the DFA we have designed will have at least 2 to the power n states, because the number of strings of length n is 2 to the power n for the binary alphabet, right? And there are more states because we are looking at strings of length less than equal n, not just equal to n. But that doesn't prove this theorem, because this theorem says any DFA. Okay. I mean, the example DFA that we have come up with, it doesn't rule out the existence of other DFAs which have less than 2 to the power n states. I mean, this is just an example DFA, right? As somebody pointed out, there could be more than one DFA for the same language. So this proposition is asserting something strong. Any DFA that you come up with for this language must have at least 2 to the power n states. Okay. So how do we show it? Well, the proof is by contradiction. And we don't have much time left, so I'll go as far as I can. So assume some DFA M accepting L has less than two to the power n states, right? Since the number of strings of length n is 2 to the n, there must be two distinct or two different strings W0 and W1 of length n, such that W Q naught W0 equals W Q naught W1. Why? Can anyone quickly say why this is the case?
Sir, then only we can have less number of states. Like for both the states, we can merge them.
Right. So if we had distinct states for every two distinct strings, right? Because the number of strings is 2 to the power n, we must have 2 to the power n distinct states, right? So this is a simple application of the pigeonhole principle. Yes. So let us proceed. Uh, let No, let me stop there. Let me stop because we are out of time. So I'll continue in the next class. Okay. Right.